Chemical reactions. So what is a chemical change and what is a chemical reaction? And how can you differentiate it from a physical change? So a chemical reaction or a chemical change only occurs when one substance is converted into one or more substance. And the new substance that is produced, it has completely different chemical formula, it has different chemical properties. Only then it is called as a chemical reaction or a chemical change. For example, if I start with water, let's say I have solid water, basically ice, and I heat it and it is converted into steam. So water as a gas. This is basically just a physical change because what we started with is H2O chemically, and what the chemical compound that we end with is also H2O. So chemically there is no difference. For a chemical reaction to occur, there should be rearrangement of atoms, meaning the atom should rearrange and form new compounds. Only then it is called as a chemical reaction. For example, if we take example of, let's say, Fe plus oxygen, when they react, it produces rust. This is an example of a chemical change. You started with atoms of iron, atoms of oxygen. Now these atoms have rearranged and formed bonds with each other. They have reacted with each other to give you a completely different compound, which is iron oxide, called as rust. This is a chemical reaction. Now there are some visible changes that occur usually during a chemical reaction, and these can act as evidence of a chemical reaction. For example, if you mix two things together and you suddenly see formation of bubbles. Bubbles would be produced when a gas would be released as a product, which means this is an example of a chemical reaction. You did not have a gas in the beginning, but once you mix the reactants together, you have gas being produced. A change in color. You started with two clear solutions, but now suddenly you have a blue color solution. That means it's probably a chemical reaction occurring. Production of a solid precipitate, meaning let's say you mix two different clear liquid solutions together and you end up with a solid as a product, meaning you did not have a solid in the beginning of your reaction, but at the end you have a solid. That is telling you it's an example of a chemical reaction. Last evidence would be heat. Heat can be produced or absorbed during a reaction. For example, let's say you mix two components into a test tube and you're holding that test tube in your hand while the reaction is going. And as these chemicals react, your test tube is either becoming more warmer or it's getting colder to touch. That probably is telling you that heat is either being produced or absorbed, and that usually occurs only when there's a chemical reaction or a chemical change. So all these four things basically tell you if a reaction is a chemical reaction or not. Example, you can see here, silver. If you let it sit outside, it kind of tarnishes. It develops this black color material on top of it. This is an example of a chemical reaction. You started with something silver, shiny, now you have something black. Similarly, iron, we know iron kind of looks like shiny metal piece, but when you let it rust in a presence of air, it usually turns into something brown and brittle. So that is also an example of a chemical reaction. Now, how do we write a chemical reaction? To represent a chemical reaction, it is usually written in form of a equation. Usually the reactants are written on the left side, products are written on the right side, and there is an arrow telling you the direction of the reaction. Example you see right here. This is an example of methane reacting with oxygen to produce carbon dioxide and water. So here we wrote the two reactants on the left, followed by products. Another couple things that you would usually see in a chemical reaction are the phases of the reactants and product. Phases, this means basically the physical state of our reactants and product. These could be anything. If it's a solid, we usually write S. If it's a liquid, it's usually written as L. If it's a gas, it's usually written as G. If it's a liquid, but it's basically liquid because it's dissolved in water, If you take salt and you dissolve in water, that gives you an aqueous solution. Aqueous is coming from aqua, that basically stands for water. So if it's something is dissolved in water, then we call it aqueous. So these are the four usual phases that you're going to find in a chemical reaction. Along with that, you might see sometimes a symbol like this, or maybe something like this, some metal or some element or some compound written on the arrow. These basically are representing different things that are involved in a reaction. For example, this triangle, it kind of represents heat is involved in this particular reaction. Similarly, if I write some kind of compound or an element on an arrow, this usually represents something called as a catalyst. A catalyst is something that just is speeding up the reaction. So it makes your reaction go faster. It is not used during a reaction, but it does participate. It's involved in the reaction, but you don't end up using this compound. So if you start with, let's say, 10 grams of a catalyst in the beginning of reaction, you will end up with 10 grams of the catalyst at the end. So it's not really used in the reaction, but it does help in speeding up the reaction. Okay, so this is how a chemical reaction would look like. And the last thing that you would see in a chemical reaction, which is very important, is that your chemical reaction should be balanced. Balancing essentially means we should have the same number of atoms of any element in the reactant side as the number of atoms of that element in the product side. So number of atoms of each element should be same on the reactant and the product side. This is obtained by balancing the chemical equation, and usually when you have a balanced chemical equation, you get a few numbers written in the front. For example, here you can see 2 oxygen and 2 water molecules. These numbers are referred to as coefficients. They are also called as stoichiometric coefficients. These basically tell you how many molecules or moles of these element or compound are involved in this particular reaction. If no number is written, that usually means it's 1. So in this chemical reaction, what it simply tells you is that if you have 1 molecule of methane, it would require 2 molecules of oxygen to completely react. And this reaction would produce again 1 molecule of CO2 and 2 molecules of water. This is what a balanced chemical equation kind of tells you. Okay. Now, next thing is, how do I know this chemical reaction is balanced? You simply count every single element that is present in a reaction, and the number of atoms that you see on the left should match up with the number of atoms on the right. For example, if I look on the left, how many carbon atoms do I have? The best way to obtain this number is that you multiply the coefficient with the subscript that you see. Okay, you remember this, we multiply the stoichiometric coefficient with the subscript. That tells you how many atoms of any element are present. So I'll write it down here. You multiply coefficient with the subscript. Okay, so if no coefficient is written, remember that's 1. If no subscript is written, remember that's also 1. For example, how many carbon atoms do I see here? It's 1 times 1, which is basically 1. How many carbon atoms do you see on the right? That's also just 1. How many hydrogen atoms do you see on the left? 1 times 4, that would give you 4 atoms. How many hydrogen do we see here on the right? 2 times 2, that would give me 4 again. So it's balanced. Last, let's check oxygen. How many oxygen atoms do I see here? 2 times 2, 4. How many oxygen do I see here in total? I have 1 times 2, meaning 2 on this, plus 2 times 1, meaning another 2 here, which gives you again a total of 4. So oxygen on the left is 4, oxygen on the right is also 4. That is called a balanced chemical reaction. Okay, now let's look at how exactly can you actually balance a chemical equation. Okay, so we'll go over some steps, and As long as you follow this procedure, you follow these tricks, you should be able to get to a balanced chemical equation. One thing I would like to mention here, a chemical equation, balancing a chemical equation is basically a hit and trial approach. So you try it out. If it doesn't work, you would have to erase everything and start from the beginning again using a different approach. Okay? But there are some tricks that help you to balance your reaction faster. So we'll just go over those tricks. Okay. For example, if we start with this chemical equation, aluminum reacts with sulfur, gives you aluminum sulfide. How should we balance it? You pick one element at a time and you start balancing and making sure you have the right number of atoms on each side. So for example, let's start with aluminum. How many aluminum atoms do I see on the left? 1. How many atoms do I see on the right? 2. The important thing here is when you balance, you cannot reduce the number of atoms. You can only increase the number of atoms. What I mean by that is because this is 1 and this is 2, you cannot reduce the 2 to 1. You will have to increase the number of atoms on the left side. The only thing you can do is increase the number of atoms. Second thing is you can never change the subscripts. Okay, if you remember from compounds, when we name the compound or write the chemical formula, every chemical compound has its own chemical formula. So if you change these subscripts, you're changing the formula of the compound, which we cannot do. So aluminum sulfide is Al2S3. So you cannot change this 2 into a 1, or you cannot add a subscript here. Only thing you can add is a coefficient in the front. Okay. So only thing I can do is if I need to change these numbers, I have to add numbers in the front, and that's it. Okay. Now I have 1 here, 2 here, which means I need 2 atoms of aluminum on the left side. How can you get it? Remember subscript. Whatever number you have here is multiplied by a coefficient. So it's multiplied by a coefficient to give you the right number of atoms. So if I want 2 as my answer and currently I have 1, what should you multiply that with to get 2? You multiply with 2. And whatever you multiply with becomes your coefficient. Meaning this is 2 goes right here in the front. Okay, similarly, let's do sulfur. So how many sulfur atoms do I have? I'm just going to do it here underneath in the space. Sulfur atoms on the left is 1. Sulfur atom on the right is 3. Again, I have to make this side equal to 3 to balance it out, which means I should multiply this 1 with a number to get 3. What would be that number? 3. Whatever you multiply with becomes your coefficient. So 3 goes right here. Oops, 3 goes right here, and that would be your balanced chemical equation. Once you have balanced it, make sure you can confirm this that it's correct. Aluminum is 2, aluminum is 2. Sulfur is 3, sulfur on the right is also 3. So now you have a balanced chemical equation. Example, let's try to balance this reaction out. So I have P4 plus Br2 gives me Pb3. If I start balancing, you pick one element at a time. For example, I'll pick phosphorus right here. How many phosphorus do I see on the left? I see 4. How many phosphorus on the right? 1. Which means I need 4 on the right side as well. So what should I multiply 1 with to get 4? I multiply it with 4, which means my new coefficient for this is 4. Next, I move on to Br, bromine. I see I have 2 atoms of Br here. And now, because you have added a number, you have to include this new number. I have 4 multiplied by 3. Remember, coefficient multiply by subscript. 4 times 3 will give me 12. I have 12 bromine atoms on the right side, which means I also need 12 on the left. So I need to make this 12 by multiplying 2 with a number. So what should I multiply 2 with to get 12? That would be 6. Whatever you multiply with becomes your coefficient. Now, I think we have balanced it, but let's confirm. How many phosphorus do we see? 4. How many phosphorus do I see here? 4 times 1, 4. Bromine, 6 times 2, 12. Bromine 4 times 3, 12. So now my chemical reaction is balanced. Let's try a couple more examples. For example, aluminum plus iron oxide gives me iron and aluminum oxide. Again, I'm trying to go over tricks using these examples. So aluminum here is 1, aluminum here is 2, which means I need to make this 2, so I should multiply this by 2, which puts 2 in the front. Next I have iron. I have 2 iron atom here. I have 1 iron atom here, which means I need to make this number equal to 2. So I multiply this by 2, which becomes my coefficient for iron. Next I go to oxygen. I have 3 oxygen atoms here, and I have 3 total oxygen atoms on the right, which means now my chemical reaction is balanced. Okay. Let's try one more example that will help you get to a different kind of a rule. This is C5H10 reacts with oxygen, gives me CO2 and water. So how many carbon do I see on the left? 5. How many carbon do I see on the right? 1, which means I should get this equal to 5. So I should multiply this with 5, and that would be my new coefficient. Hydrogen is 10. One thing I would like to mention here, you see how oxygen is present in one of the reactants and then it's present in 2 products. So the order that I would usually like to pick my elements when balancing is that I would like to pick the elements that are only present in 1 reactant and 1 product. For example, I would not like to pick or begin with oxygen. Why? Because it is present in 1 reactant but 2 products. So if it's present in 2 reactants or 2 products or more than 1 reactant or product, it kind of makes it a little difficult to balance those elements. So usually you should save those elements for the end. Balance every other element out and then wait and do the balancing of the last element at the very end. Okay, so for example, here I don't want to pick oxygen. I'll pick hydrogen first. I have 10 here and I have 2 on the right side. So which means I need to make this equal to 10. So what should I multiply with? I should multiply with 5. So that would become my coefficient right here. Next, I move on to oxygens. So when I look at oxygen, I have 2 oxygen atoms on the left and I have 5 multiplied by 2. That gives me 10 here and 5 here multiplied by 1. Total is 15. So now I need to make on the left side also 15, which would give you what should you multiply 2 with? If you multiply 2 with a 7.5, that would give you 15. Okay, one thing though with stoichiometric coefficients is that all your coefficients should always be whole numbers. We never include decimals or fractions here, but this is kind of like a trick, like I mentioned earlier. If an element is present by itself, meaning it's not making a compound. For example, oxygen here is present by itself. It's not water. It's not making any other compound on this left side. Then you can use a fraction to begin with, and then we'll balance it out to get rid of that fraction. So again, this is a trick and it only works if you're trying to balance an element which is present by itself. What do I mean by that? For example, this is O2 by itself. If, for example, let's say this was MgO, meaning oxygen with magnesium, then you cannot use this trick. Then you have to use something else. But for now, because this is by itself, I'm just going to simply put a 7.5 in the front as my coefficient. A little less space, 7.5 O2. Now, like I said, we cannot have fractions or decimals here. So what is the best way to get rid of a 0.5? If you multiply 0.5 by 2, that would give you 1. It would simply convert your decimal into a whole number. So I can multiply this 7.5 by 2 and that would give me a whole number. But I cannot just multiply one of the elements in the reaction. I have to multiply the whole reaction by 2. Okay, if I do that, what does it give me? It gives me 2C5H10 plus 7.5 times 2 will give me 15O2 produces 5 times 2, 10 CO2 plus 5 times 2, 10 water. So this is now my final balanced chemical reaction. You can keep going back and forth if you try to balance this out without using this trick. It would just take you longer. You can balance it, but it would just take you longer. So this is kind of like a trick to help you balance it faster and reach to your answer faster. Okay, so if you have a situation like this, you simply use the decimal and then you can get rid of the decimal by multiplying the whole equation by a number to change it into an actual whole number. Another thing that I would like to mention, how do you know these coefficients are good? Your stoichiometric coefficients should always be the smallest ratio possible. So 2 is to 15 is to 10 is to 10. I cannot go any smaller than that. And all of these are whole numbers. So that would be my final answer for this particular reaction. Okay, next you would also find some chemical reactions like this. If you remember, these are called as polyatomic ions. How do we balance them? Again, I'll give you a suggestion, okay, for this. Lot of times you can, if you want, you can balance sodium separately, phosphorus separately, oxygen separately, but that would take you too long. So one easy way to balance reactions with polyatomic ions is, for example, if you have a chemical reaction, in this, if I look here, I have PO4, and this PO4, I don't see phosphorus anywhere else in my reaction. All the phosphorus is present as PO4, which means this PO4 is staying together. It's not breaking apart. If your PO4 is not breaking apart, then there's no need for you to break it apart. You can keep it all together. Balance it as one entity. Okay? Instead of balancing phosphorus oxygen, just balance PO4. So let's try and balance this out using this approach. We can start with whichever element. Sodium, I see I have 3 sodium here, I have 1 sodium here, which means I multiply this by 3, so I put a 3 right here. Next I see phosphate. Again, I'm not going to balance P and oxygen, I'll balance the whole thing together. How many PO4 do I see? I see 1 PO4 on this side, I see 2 PO4 on this side, which means I need 2 PO4 here, so I'm going to make this 2 in the front. But now you notice, as soon as I added a 2, I added this 2 in front of sodium as well. So that changes my number of sodium atoms as well, which means I need to get rid of this sodium that I balanced earlier, and I'll have to repeat it. Okay, so you might have to go back and forth if you change these numbers during balancing. So now if I go back to sodium, I have 2 times 3, 6 sodium. Here, oh, I forgot to get rid of this 3. Here I have 1, which means I should multiply this by 6 to get 6 to balance it out. So I put a 6 right here. Phosphate is still 2. Phosphate is still 2. Magnesium here is 1. Magnesium here is 3, which means I multiply this by something to get 3, and that would be a 3. Next I look at chlorine. Now chlorine on the left side, 3 multiplied by 2 is 6. Chlorine here is 6 multiplied by 1, that is 6. So now my chemical reaction is balanced. Again, this is in this type of reaction, if you have polyatomic ions, observe if your polyatomic ion is staying as one entity. If it is, balance it as one entity. Don't break it apart. Okay, there are some examples here which you guys can try on your own. Let's try one example, maybe this aluminum. Let's try the third one. Aluminum atoms that I see here is 1. Aluminum that I see here is 2. So let's put a 2 in front here to balance it. Now going to hydrogen, I see 2 here and I see 2 here, balanced. Next go to sulfate. Again, this is a sulfate polyatomic ion. Instead of doing S and O, let's see, is there S and O breaking apart in the product side? No, it stays as SO4. This is SO4. So let's balance it as one entity. So how many SO4 do I see here? Just one. How many SO4 do I see here? That would be 3, which means I need to make this 3. So I put a 3 right here. Now, because I added a 3, that changes my hydrogen. How many hydrogen do I have here now? On the left, 3 times 2, 6. How many do I have here? 2, which means I need to make this 6. So I should multiply 2 by 3, which means I put a 3 right here. Let's confirm if everything looks correct. 2 aluminum, 2 aluminum. 3 times 2, 6 hydrogen, 3 times 2, 6 hydrogen. 3 times 1 sulfate, 3, so that's 3 sulfate, and this is also 3 sulfate. So that is my balanced chemical equation. If nothing is written, that automatically means it's just 1. So the coefficients are 2 is to 3 is to 1 is to 3. 2, 3, 1, 3 is B. Okay, now let's quickly look into different types of chemical reactions. So we just saw how to balance these reactions. Now let's classify these reactions. There are 5 major classes of chemical reactions: combination, decomposition, single replacement, double replacement, combustion. It's pretty easy to kind of remember them. Their name tells you exactly what happens in this reaction. So let's look at them. For example, first one is combination. What is a combination reaction? Where things combine. This is also called as synthesis reaction. Synthesis means you're forming something new. Combination means you're combining few things together. So if you have 2 reactants and they are giving you one product, meaning they are combining with each other, that's an example of combination. Example you can see right here. 2 or more reactants give you one product. Decomposition is opposite of that. Decomposition means they are decomposing. So you start with one reactant, but it breaks and gives you more than one product. That is decomposition. Example like these. Single replacement. A single replacement reaction is, for example, if I react A with a compound BC, and here it gives me product AC. How? Initially B is made a compound with C. Here A is by itself. Now A will kick B out of its spot and it will make a compound with C, which is AC, and B will be left alone in the product. This is single replacement. When one element replaces another element from its spot, that is called single replacement. Example you can see here, zinc is reacting with HCl. What you see in the product is zinc with chlorine. Initially zinc was by itself and hydrogen was with chlorine. Now in the product zinc is with chlorine and hydrogen has been kicked out. Hydrogen is by itself. So zinc replaced hydrogen. So this is called single replacement. It is also called as displacement sometimes. So single replacement or single displacement. Next we have double replacement. In this case AB is reacting with CD. So whenever you have 2 compounds reacting with each other, these are 2 different compounds, not an element, compounds. A in this case in the reaction is with B and C is with D. But if you look at products, A is with D now. So A is making a compound with D and C is making a compound with B. So when 2 elements are displacing each other, those are called as double displacement or double replacement. Again, displacement or replacement. Then lastly, we have combustion. Combustion is when you're basically burning something out in presence of oxygen. Most of the times the reactions consist of a hydrocarbon, which is basically a carbon and hydrogen compound, because these usually act as fuels. And one of the important reactant here is oxygen. So this would react with oxygen to give you CO2 and water. Carbon will be reacting with oxygen to give you carbon dioxide. Hydrogen will be reacting with oxygen to give you water. This is an example of a combustion reaction. So these are these 5 different type of chemical reactions. More details and everything that I just mentioned is also listed on your slide. So details about combination, decomposition, some examples, what exactly are these? They're all listed in this slide. Okay. I'd like to add a little more information here. For example, there are some more categories or some more subcategories for these reactions. And one chemical reaction can belong to multiple different categories at the same time. Okay? So what do I mean by that? For example, if you take this chemical reaction, if you look at this chemical reaction and we try to identify, we can see here this is potassium with iodine in the beginning. As a reactant, lead is with nitrate, but when you look at products, now lead is with iodide and potassium is with nitrate. So basically they switch their partners kind of. Potassium is with nitrate, lead is with iodide. This is an example of a double displacement reaction. At the same time, this reaction is also called as a precipitation reaction. What is a precipitation reaction? When you mix two aqueous solutions, you can see these two reactants are aqueous, meaning they are dissolved in liquid. So here is one of the examples of these. So this right here is Ki in the beaker, and what's being poured here is basically lead nitrate. You can see this is a clear liquid, this is a clear liquid. When I say clear, I don't mean colorless. I mean clear, meaning transparent. You don't see any kind of solids here. It's not opaque. You can see through these liquids. So those are these two reactants, both aqueous. But when you dissolve them, when you mix them together, you see something solid is being produced. It doesn't look like solid here, but if your solution starts turning turbid, meaning it's looking milky or it's looking cloudy, it's looking opaque, it is looking like a colored solution which you cannot see through. For example, this portion you cannot see through this. This is not transparent. This is not clear. This essentially means you are producing something solid. It is just a very fine solid, but basically this is solid. So if you let this sit, all this solid is going to settle down in the bottom. So this solid being produced is PbI2. Like you can see here, this phase is written as solid. The other product is aqueous, but there's one solid being produced. Such reactions where you mix two clear solutions together and it produces something solid and the solution becomes opaque are called as precipitation reactions. And this solid that is produced, this is called as the precipitate. So these are some terminologies that are commonly used. Double replacement reactions that form solid products, which are called precipitates, are called as precipitation reactions. So double replacement reaction can also be like precipitation reaction is also a type of double replacement. So like I said, there are some subcategories as well. Okay. Let's look at a couple more subcategories. Another example is acid-base reaction. These are also double replacement reaction. What are acids? An acid is a compound that is usually written with hydrogen in the beginning. So if you remember from naming, we saw some acids, HCl, HBr, these are all acids. A base is a compound that usually consists of OH in it, a hydroxide. Okay, acids usually like to donate their hydrogen. Bases usually like to accept that hydrogen. Whenever you mix acid and base together, they will always produce a salt and water. That is what they usually produce, acid plus base. For example, if you look at this reaction, HCl plus NaOH, how would they react? If you have two ionic compounds reacting with each other, most of the times, how can they react? They are going to do a double displacement reaction. Okay? If ionic compounds, for example, like this, well, this is molecular, but if you have like two aqueous solutions that can form ions, so this is can form ions in water, then they are going to react by double displacement, meaning the hydrogen from the first is going to make a compound with OH from the second compound. Cation of the first, anion of the second. Hydrogen will make a compound with OH, which is HOH, which is water. And then whatever's in the middle, They are going to make a compound with each other. So Na and Cl will make a compound NaCl. What is this? This is salt. And what is this? This is water. Oops, water. So acid and base usually react to give you salt and water. Another example is this. Again, H2SO4 is an acid. It would react with KOH with the base. So H and OH will make a compound which is water, and K and SO4 will make a compound which is K2SO4, which is a salt. So this is an example of double displacement, but specifically these are called as acid-base reactions, which are also called as neutralization reactions. Neutralization reaction is another name for acid-base reaction. Why? Because here you're neutralizing the acid by adding base. So this was an acid before. Now what you have in the product is basically water. There's no acid left. So what did you do to this acid? You neutralize the acid into water by reacting it with the base. That is why this is also called as neutralization reaction. Combustion. Okay, so example could be like these. For example, this reaction, classify these reactions. Aluminum plus H2SO4 gives you Al2SO4 whole thrice. So what is happening here? This aluminum is making a compound with SO4 in the product, and hydrogen is being kicked out. So this is single replacement. Here sodium is with sulfate, and now silver is with sulfate in the product, which means sodium is with probably nitrate and silver is with sulfate. So this is double replacement. Nitrogen and oxygen are combining to give you nitrogen monoxide. This two reactants, one product is combination. Next, C2H4 plus O2 is giving you CO2 and water. So remember, whenever it's a carbon hydrogen compound, mostly, but important thing is there has to be oxygen as one of the reactant. Oxygen has to be one of the reactant. For example, for a flame, oxygen is needed. Without oxygen, you don't have a flame. So that is an example of combustion. Next, I see this K2CO3 is breaking to give me two compounds. I started with one reactant, but I have two products, which means it's breaking. So this is decomposition. Okay, moving on, another subcategory of these chemical reaction, which is the last one, is called oxidation reduction reaction. Oxidation reduction reactions are also abbreviated as redox reactions. What are redox reactions? These reactions involve transfer of electrons. Here electrons are transferred from one substance to another. For example, A and B will react to give you A here has this electron, B here has no electrons. I mean, not that you see here. A is going to give its electron to B, and now B has the electron, A doesn't. So when one compound transfers its electrons to another substance, that is called oxidation reduction. These reactions are called redox because they consist of two steps. One is called the oxidation half of the reaction. Another one is called the reduction half of the reaction. The two reactions are occurring simultaneously. One reaction is oxidation, another reaction is reduction. They are also called as half reaction. But important thing is they always occur together. Both of these reactions have to occur together. Only then an oxidation reduction reaction will occur. What is oxidation by definition? Oxidation is loss of electron. So whoever lost the electron is oxidized. Example here, A lost this electron. A had the electron, in the product A doesn't have the electron. So A lost its electron, so A is oxidized. B did not have an electron in the beginning, but now in the product it does, which means B is reduced. Whoever gains the electron is reduced. Reduction is gain of electrons. One easy way to memorize this definition is, if you can remember oil rig. OIL stands for oxidation is loss of electrons. And remember, only electrons are involved here. RIG stands for reduction is gain of electrons. So that's one easy way to memorize these definitions. Now, how can you tell if this is an oxidation reduction reaction, or how can you tell who is oxidized and who is reduced? One easy way to tell that is by checking their oxidation number or oxidation state of each element. Okay, in your case, we are just going to stick to like easier examples. So for you, oxidation state essentially is same as the charge on an ion. Okay, for example, aluminum here. What is the charge on aluminum here? It's by itself. If nothing is written here, that means it is 0. Aluminum is 0. Whenever any element is present in its natural state, meaning aluminum is Al, copper is Cu, iron is Fe, when they are present by themselves in their natural state, their oxidation state or charge is 0. So for example, aluminum here is 0. Chlorine here is also 0. Chlorine, nitrogen, hydrogen, oxygen, fluorine, chlorine, bromine, iodine. 1, 2, 3, 4, 5, 6, 7. These 7 elements are the ones that exist as, oh, Br2, sorry. These 7 elements exist as diatomic molecules. So when they are present in this form, their charge is also 0. This is their natural state. So that is why Cl2 is also 0, because chlorine in its natural state exists as Cl. So it has no charge. When you make it a compound, remember a compound, this is ionic compound, so we can figure out what is the charge. Aluminum and chlorine. What is the charge that aluminum usually carries? Aluminum 3+. Chlorine usually carries a charge of -1. Again, this is a compound. That is why these elements are carrying a charge. When these are elements by themselves, these elements don't carry any charge. So what happened to aluminum? The charge was 0. Now it is 3, +3. How would it get a charge of +3? It would only get this charge if it loses electron, meaning aluminum lost 3 electron, and loss of electron is oxidation. That is how I know aluminum is oxidized here. Chlorine, the charge is 0. Here the charge became -1. How would it become -1 from 0? It has to gain 1 electron. Every electron gained is a negative charge. Every electron lost is a positive charge, right? So electron is gained here. That is why this is called as reduction. Remember, electron has a negative charge. This is electron. So if you gain an electron, it would add a negative charge because electron carries a negative charge. If you lose one electron, that would, oh, if you lose one electron, meaning you lost the electron, so that would lead to a positive charge. You lost one electron, so you lost the negative from it. So what's left behind is basically positive. Okay, so for example, you can see another example here. This is a chemical reaction. What is the charge of copper here? Sulfate is 2-. So if you remember, I can assume copper is X plus -2 from sulfate because SO4 is 2- charge. Total is 0. So X is +2. So charge on copper here is +2. Charge on zinc here is 0. And I'm only looking at these elements here because why? SO4 is SO4. Nothing has changed here. So SO4 was SO4 2-, SO4 is SO4 2- in the product. That is why I'm ignoring sulfate. Zinc on this side now is in a compound. What is the usual charge that zinc has? 2+. Copper here is by itself, meaning what is the charge? 0. So now if you look at copper, copper went from +2 to 0, meaning it was a charge of +2, now it is 0. How? It must have gained electrons because of which the positive charge was neutralized. That is why it gained electrons, so this is called reduction. So in this case, copper is reduced. Next, zinc was 0 and now it has changed to 2+, meaning it was 0, it has a positive charge, so it must have lost the electron. So zinc here is oxidized. Majorly, in your case, I'll probably not give you reactions. I'll probably give you something like this, where it's easier to tell if it's oxidized or reduced. For example, tin is changing to tin 4 plus and 4 electrons are lost. Okay, it was tin, it was one thing before in the beginning, but it broke to give you two things, which means this was broken apart, it was lost, and it has a positive charge. So this is loss of electron, which is oxidation. Iron 3 plus plus 1 electron became iron 2 plus, meaning it was a charge of plus 3. Now it's a charge of plus 2, meaning it has reduced the positive charge. How? It must have gained an electron. And you can see here, these iron combined with one electron and it gave you this. So this is gain of electron, so it is reduction. Next you see here Cl2. It is also gaining an electron. When you're gaining electron, meaning it's adding, these two electrons are being added to Cl2. This electron is being added to this. Okay, whereas here tin is breaking to give you two things. The electron broke off, so it lost it. This is gaining. You're adding the electron, right? The plus sign here. You're adding it to chlorine, which means this is gaining electron again, so this is reduction. So if your electrons are on the reactant side, that means you're gaining electrons. So it is reduction. If your electrons are on the product side, meaning you got rid of this electron, it's a product. It was with you first, now you have lost it. So it's a product, that means it has lost the electron. So this is oxidation. That's one way to recognize oxidation and reduction.